Welcome back to the first really new chapter of this course, namely the chapter called Linear Maps. As I promised you, we now want to study maps between vector spaces, and the main idea or the main philosophy behind this is that so far we have seen vector spaces as sets with additional structures, namely with an addition of vectors and scalar multiplication. So this was some kind of additional structure. Now linear maps should be those maps which are not just arbitrary maps between these vector spaces, but maps between vector spaces that respect these structures. So they kind of respect the addition and the scalar multiplication of these of the vector spaces involved, of its domain and its codomain. And this is precisely what's formalized in this definition, and I will start straight away with the definition. Just one thing. I don't want to write all the time that everything takes place over a field K, because I just consider a fixed field in vector spaces over some fixed field in this section. So throughout this section, let K be a field. So we just fix a ground field and work with this. Okay, definition of a linear map, definition 7.1. Let V and W be vector spaces over K. So over the same field K. A map F from V to W is called a linear map, or some other word that's often used, homomorphism. We'll mostly stick with the term linear map, but if you read about homomorphisms in some textbook or lecture notes or something, this is just another word for linear map in this case, if you talk about vector spaces. Now, what does this mean? I said it should respect the structures. So, first thing, if I take the sum of two vectors in V and apply F to this sum, the result should just be the sum of the different values of F on these vectors, which means this should be the same as F of V1 plus F of V2. So sums are mapped to sums. That's the idea here for all V1, V2 in V. And secondly, the scalar multiplication. So if we take a vector V in the space, in the vector space capital V, and multiply it with some scalar lambda, so this is just multiplication with an element of the field. We also want it to respect scalar multiplication, so the result should be lambda times F of V. So scalar multiples are mapped onto scalar multiples. That's the idea. And this should be for all lambda in K and V in our vector space V. So this is scalar multiplication in V, this is scalar multiplication in W, and the same way this is the addition in V, this is the addition in W. So they are interchanged with one another. Sorry about the sudden cut, I just forgot to introduce a piece of notation and already wanted to go on with the next remark. So this is a linear map, and the set of all linear maps between two vector spaces. So the set of all linear maps from V to W is denoted by, so two possibilities. Either you write L of V comma W, L like linear of course, or if you take the homomorphism viewpoint, another way of writing this is hom V W. And in different textbooks you might find different notations or even completely different ones, but these are the most common ones. Okay, so this is just notation for the set of all linear maps. Now, I want to summarize a few simple properties of linear maps in a remark where we just discuss some consequences which follow really straight away from these two properties 1 and 2. So, first of all, again, VW should be again vector spaces over K. And let's use this notation for the first time. We take F as a linear map from V to W. So, first of all, if we iterate the properties 1 and 2, we can have an interesting consequence. And by iterating, I mean the following. Assume we don't have just a sum of 2 vectors or scalar multiple of 1 vector, but just some combination of the 2. So we have some vector of the form, let's say from I equal to 1 to n, lambda I times vi. So a linear combination of, an arbitrary linear combination of the vectors v1 to vn. Now, if we apply f to this, and now we can use these formulas here n times basically. So first of all, we take the last summand and apply this property 1, then takes the next summand, apply property 1, and so on and so on and so on. And then use the compatibility with scalar multiplication. And if you really think about this, this is kind of quite instructive to write this down on your own, so I won't discuss this too much, and maybe hit the pause button and now write this down for yourself. This is then easy to see that this is nothing but the sum from 1 to n of lambda I times f of vi, simply by just using the above properties over and over and over. And this holds true for all lambda 1 to lambda n in k, v1 to v1 n in v. So this will be used many, many, many times. So let me just put a box around this, because this is just important, because this formula is used really all the time. Okay. So this is the first thing that's easy to see. The next thing, which is not that, maybe not that obvious, but also easy to discuss, is that we already know one value of each linear map, namely each linear map satisfies f of 0 is equal to 0. So this is the 0 in the vector space V. Let me just add this, so I hope you can recognize this. So 0 as an element of V, and this is now the 0 element of W, of course, but always the 0 element is mapped onto the 0 element. Why is that? We know that f of 0, now the 0 vector can just be written as 0 plus 0. Okay, this is not too exciting, but now we've got here the sum of 2 vectors, so we can use this property 1 of linear maps and get that this is f of 0 plus f of 0, which is equal to 2f of 0, of course. And of course, now we have seen that f of 0 equals 2f of 0, and this is only satisfied if f of 0 is 0. So this already shows this property. Okay, so this is something we should always keep in mind. 0 is mapped onto 0, so it's in that sense, the linear map is even preserving more structure of the vector space, namely a 0 element. This is always kept and preserved under application of linear maps. Now, third thing, just definition. If we have infinite dimensional vector spaces, we will talk about linear maps and dimension later on in much greater detail, but if both of them are infinite dimensional, there's another name for this. F is also called an operator. Operators, so linear maps between infinite dimensional vector spaces, are basically part of functional analysis, and they will be probably much more discussed in Math 3 or Math 4. I don't know the curriculum there in detail, but at some point you will also learn more about these operators. But in this lecture we shall so far mostly discuss linear maps between finite dimensional vector spaces, and this is just to let you know the name operator, so if at some point you read this word, you know what it is. Okay, now this was the remark. Let's do some examples. Okay, and as always, we start with a stupid example, namely the first one. So if V, W are arbitrary vector spaces over K, then there's a very obvious, two very obvious linear maps, namely Z, the map which goes from V to W, which maps just everything onto 0, is linear. Oh, really? So this is really easy to see, because if everything is mapped to 0, these properties follow almost straight away, so there's nothing to discuss. And another map which is not too exciting, the identity map. ID index V. So the identity map is always defined by just mapping everything onto itself. This is a linear map. So this is linear. And this is also trivial because this would basically mean we can forget about the F because everything is mapped onto itself. And then it already stands there. So there's nothing to discuss here basically. Okay, now that we've got the trivial stuff out of the way, let's do some more interesting things. The most basic, maybe the easiest linear map, which is not trivial or which is quite interesting, is the following. Let V again be a vector space over K, and take A to be a fixed element of K. Then F going from V to V, so just one vector space and we stay within itself. F of V is scalar multiplication by A times V. This is a linear map. And let's do the computation just to see how this follows. So if we have the sum of two vectors, f of v1 plus v2, so this is just by definition a times the sum of v1 and v2, but this is definition of a vector space. We have this distributivity property. So the scalar multiplication is distributive with respect to the sum, meaning that this is the same as a times v1 plus a times v2, and this is by definition just f of v1 plus f of v2. And okay, now the scalar multiplication, if we have f of lambda times v, this is the same as a times lambda times v. But since we are talking about a field, the multiplication, so this would be, sorry, I have to be precise with this. So this would be kind of formally the definition here. But we've seen about the scalar multiplication that it has some associativity property, meaning this is the same as a times lambda. So this is multiplication in the field. So in the field K, this multiplied with V, but we've seen that, so just by definition, the field, the multiplication is commutative. So this is an abelian group with respect to multiplication, meaning that this is the same as lambda times A times V. And now I can use the associativity again. So this is just combining field properties and vector space properties. Now this is the same as lambda times A times V. And now we see what's that? This is lambda times f of V. Okay, and this holds, of course, these properties for all V, V1, V2 in our vector space V, and all lambda in K. So this is just very easy. So of course, later on we won't do this in this excessive detail. So this was just very, very detailed about the different steps, but yeah, we won't be that detailed always. That's quite enough to use. These things could actually be used without arguing. Okay, so this is the easiest thing. So multiplication with some constant. Scalar multiplication is a linear map, which is kind of intuitively clear because kind of when you think about high school mathematics, for example, or what you think about linear maps, this was basically lines or you had planes in mind or something, and this is always something where, this linear map, like linear from the real numbers to the real numbers, would also just be multiplication with a constant, as we learned in high school, and so this is just generalizing this idea of a linear map. So, I mean, this is good because kind of if this wasn't linear by definition, then we would have a very bad definition of linear maps. So this just shows that, yeah, this definition is kind of intuitively what we expect. Now something slightly more complicated, which is yeah, basically a very special case of something that we will see in much more detail later. Just to give you an example how higher dimensional things could look like if we consider namely the space R2. And we consider this, of course, as a real vector space. So a vector space over the field of real numbers. Then we get the following then, just as an example, the map F going from R2 to R2, which takes x, y, and maps this onto 2x plus y, I took as an example, and x minus 5 y in the second coordinate. So this is, again, in both components, it's just a linear combination, basically, of these numbers x and y. And this means that this is, again, a linear map. So this is a linear map. And this is something you can just compute explicitly, which I would do after erasing. Okay, let's do the computation. If we take two elements of R2, let's call them x1, y1 and x2, y2. So let's compute f of the sum of x1, y1 and x2, y2. If you recall, the sum on R2 is just defined component-wise as the vector space addition. So this is just f of x1 plus x2, y1 plus y2. Now we can just insert the definition of f. So just by definition, this is the same as 2x1 plus x2 plus y1 plus y2. So twice the x component plus the y component. And in the second, we have the first coordinate, so x1 plus x2 minus 5 times the second component, y1 plus y2. So let's do this computation and reorder the terms a bit. Namely, this is the same as 2x1 plus y1. So just taking first this sum and then this one, and the rest that remains is 2x2 plus y2, and let's do the same here. x1 minus 5y1 plus x2 minus 5y2, and now we can put it apart into two summands as follows. This is 2x1 plus y1 comma x1 minus 5y1 plus 2x2 plus y2 and x2 minus 5y2. And this is just by definition the same as f of x1 plus y1. F of x1 y1 plus f of x2 y2. And this works. So f of the sum is the sum of the values of f. This is what a linear map does. Now for the second property, this is checked on the same lines. I will skip this computation. You find it in the lecture notes. So, but this is really elementary. So nothing very exciting happening there. So this is just a simple computation. Okay, so this is a really elementary example of a linear map from R2 to R2, and we will later on see the general form of a linear map and how this arises and how this is a special case of a much more general construction. Okay, so another example. So I claim that we've already seen linear maps in Mathematics 1. Not only in my course, but also if you attended Mathematics 1 with some other lecturer, this should have been there. The problem was just that you didn't code it this way. Namely, the following. We consider the field to be either R or C, and we let I be an open interval. Okay, now I'm using notation I introduced in the last week of Mathematics 1. Namely, we consider the following map, which goes from the space C1ik. This is the space of continuously differentiable functions on the interval I with values in k, so either R or C. So functions from I to k which are differentiable and whose derivative is continuous. This map goes to the space of continuous functions on the interval with values in k. So it's this notation that I used. And I want to consider the following. D of f is just the derivative of f. That's why I call it D. So we just associate with each map its derivative, and since C1 by definition contains those maps which have continuous derivative, this is really well defined. And I should mention this. This is what I did also in the last weeks of the previous semester. These two guys are real k vector spaces, vector space over k, namely by just pointwise addition of functions and scalar multiplication. This is what you intuitively do when you add functions. So this standard addition and the multiplication by constants, this turns them into vector spaces. And now I consider this map going from here to there. And this map D is a linear map, and I claim there's nothing to do because I've already proven it. We have seen that, so what does this mean? So for the first property, the derivative of the sum of two functions is, as we've seen, the sum of the two derivatives, which is just the linearity we need here for the compatibility of D with additions. Also, the derivative of a constant multiplied with a function, it's just the derivative multiplied by the same constant. This means that this map D is compatible with the scalar multiplication, so this shows the second property of linear maps. And this was shown, so in my lecture notes from the previous term, that was theorem 4.9a. I think I called this already linearity at that time without telling you why, but here's now the reason. So this really shows that this is a linear map. And for this construction, see, this was, just if you can't remember, this was example 6.7.5 in my lecture notes from the previous term. Okay, so this map is really a linear map, which is kind of fun fact somehow, because if you think about vector spaces, you don't think about these automatically, but this is a very useful property that we shall also need later on. And now a similar construction from the previous semester, and maybe you might guess what's coming. Take A, B, and R with A smaller than B, and we consider the following map. We take the integral, namely the map, or we call this I, going from the space of Riemann integrable functions on the interval RB. This was my notation for the space of Riemann integrable functions. Going to R, which just associates with each function the value of its integral. So I of f is the integral from a to b f of x dx. This is just a number which we compute, so we really have the boundaries here, so really evaluate this as a number. This map is linear. Again, this is a vector space which I've shown also like in, I think in the same example, maybe 1 point later or earlier, I don't recall. Anyway, this is a linear map. And this we've already seen, because we know that the integral of a sum of two functions is the sum of the integrals, and we've also seen last semester that the integral of something multiplied by a constant, we can just pull the constant out of the integral. This is the standard computation rules for integrals, and they then, if we reformulate these standard computation rules in a fancy way, we can say that this map here is linear. So this was theorem 5.11a and b. In my notes from the previous term. So this is where I proved that the integral of a sum is the sum of the integrals and the same with the constants. So this is now kind of more fancy example of a linear map. Now, just to complete this, let me give you an example of a map which is not linear, although you intuitively might think this at first sight. So a counter example. I mean, there are many maps which are not linear. So if we just take some arbitrary vector space over K, vector space over K, and we fix an element V0 in this V with V0 not equal to 0, then the map, which goes from V to V, which just takes f of v to be v plus v0, is not linear. So geometrically in Rn, this would just be the translation. So we shift everything towards the direction of v0. This is the idea here. This is not linear. And just to show this, we just need to show that one of the properties is violated. So let's take the sum property. If we take f of v1 plus v2, this is by definition v1 plus v2 plus this fixed vector v0. Okay, but let's do it from the other side. Let's check the other way. So we want f of v1 plus f of v2. Now, here we add v0 and here we add v0. So the result is v1 plus v2 plus 2 v0. And since v0 is non-vanishing, this cannot be the same. Right? We can just subtract v1 plus v2 plus v0 on both sides of this equation if this would hold, and then we would get as a result v0 equal to 0, which is a contradiction. So this property is violated, so this map can possibly be linear. Okay, so adding constants or just shifting constants, this just destroys everything. Also, since we've seen, this would be kind of the easiest way to prove this, we've seen that linear maps always map 0 to 0, but obviously if v is 0, the result is v0, which is non-zero. So this is already a contradiction at that point. Okay, so now we've seen the definition, we've seen some very easy consequences and some examples, and now we shall explore the properties of linear maps and see what they do and how we can kind of study them and what's special about them. First of all, the good news, same as for differentiable functions, continuous functions, and so on. Sums of linear maps are again linear, and scalar multiplications as well. So assume that V and W are vector spaces over K. Just some arbitrary vector spaces. If F and G are maps from V to W, which are linear, then their sum, F plus G, from V to W is linear. Oops, linear. Secondly, if F from V to W is linear, and we have a fixed constant lambda in K, then lambda F, so the pointwise multiplication with lambda as a map from V to W is linear. And now you might also think, okay, we've got now the sum of linear maps and scalar multiplication, we've got this as well. Now, what we namely get then, moreover, if we take all linear maps, L from V to W, we take the pointwise addition, so with addition and scalar multiplication, so the two things that we had just introduced here, this is again a vector space over the K, of course. So the space of all linear maps from one vector space to another vector space is itself again a vector space, which is quite interesting, I think. Okay, let's check this. Okay. I will only do the proof of part A because it's kind of, it's always basically the same computation, so I think it's not that instructive. So let's do A. So let V, W in V and lambda in K. Then we have to check that the equations that we need will hold at this point, since F and G are linear. We can compute the following. So we need to show, and now we just need to basically sort things out what we need to show. So the sum F plus G needs to be linear. This means the sum of V plus W of this sum has to be V plus G of V plus V plus G of, F plus G of V plus F plus G of W. So this, first of all, by definition of the sum of maps is nothing but F of V plus W plus G of V plus W. And now we need the linearity of F and G, because this now implies, since F and G are linear, this one here is F of V plus F of W, and same here, this is G of V plus G of W. Okay, now let's just rearrange things. This is the same by just reordering the terms as F of V plus G of V plus F of W plus G of W. And just by definition of the sum of maps, now just in reverse, this is the same as F plus G of V plus F plus G as a map of W. Okay, this is what we wanted. The same way now with the constants. So I've already introduced this lambda. F plus G of lambda times V. This is now by definition, f of lambda times v plus g of lambda times v. And now again, f and g are linear, so we can just pull the scalar multiplication here out. So this is the same as lambda times f of v plus lambda times g of v, which is, of course, if we just factorize out this lambda here, so distributivity, lambda times f of v plus g of v. And now we're getting somewhere because this is, of course, the same as lambda times f plus g of v. Okay, and these two properties then show f plus g is linear. So the sum of linear maps is linear. Okay, let me erase and then conclude the proof of this statement. Now, part B of the statement can be shown by basically very analogous computations, and I will just skip this proof because this is really not very difficult. So this is just standard computation, so B is shown analogously. Now for the linear, for the vector space part of the space of linear maps. We've seen before, so by example 672 in the finish of the previous semester. So the space of all maps from V to W, which I was denoted by like this, so V to the W to the V, so the space of all, the set of all maps from V to W is a vector space over K. And now if you think about properties A and B, so we are already inside, so the linear maps are of course elements of this thing. So by properties A and B, what we've basically shown is precisely the linear subspace properties. So by properties A and B, which we have proven at this point, L of VW is a linear subspace. Of W to the V. And since every linear subspace of a vector space is itself a vector space, this is all we needed to show. So hence, it is in particular a vector space over K if we forget about all the rest of the maps. And this already suffices to show the proof. So the space, the set of linear maps from V to W has a vector space structure. Okay, now another property of linear maps, theorem 7.5. Now we need three different vector spaces, so U, V, W should be vector spaces over K. Oops, sorry, handwriting is even lousier than usual, sorry about that. If we have vector spaces and we have this time two linear maps, namely F from U to V and G from V to W linear maps, then I think had similar results for continuous functions, differentiable functions and so on in the previous semester. Now everyone can guess what's coming. The composition of these two maps, G composed with F. So first F goes from U to V, then G goes from V to W. So the composition goes from U to W. This is again a linear map. Okay, so the proof is again an explicit computation. Proof. Okay, first of all, we take two elements V1 and V2 in U. So then if we compute this composition, G composed with F of V1 plus V2, so we have to show that this composition is compatible with sums. Now by definition, this is just G of F of V1 plus V2. Okay, and now here's F of V1 plus V2, and since we already know that F is linear, this means that this is the same as G of F of V1 plus F of V2. Now this is again G of the sum of two vectors, and so we can now use the linearity. Somehow word that's hard to produce, hard to pronounce for Germans. I don't know why, but anyway, linearity. So by the linearity of G, this is the same as G of f of v1 plus G of f of v2. And now by definition of the composition, this is G composed with f of v1 plus G composed with f of v2. And this is what we wanted to show. Okay, now for the second property, we take v to be an element of u and lambda to be an element of k. Then, and now it's really, basically the same computation. We take the composition G composed with f of lambda v. This is G of f of lambda v. And since f is linear, we can just pull this scalar multiple out of the f. So f linear, this is G of lambda times f of v. Now we can use that G is linear, so we can put the scalar out of this one. So this is lambda times G of f of v, which is lambda times G composed with f of v. So this shows the two properties, so it follows that G composed with f is a linear map. This might be the least exciting proof of the whole semester, but this is just, linear algebra involves a lot of explicit computations in here, so this is kind of what makes it somehow easy to understand, but somehow also quite boring. Anyway, that's just personal opinion. So, we've seen that compositions of linear maps are linear. Now, another property of linear maps, which is really useful in what's to come. So theorem 7.6, that V and W again be vector spaces over K, and F be a linear map from V to W. Okay, just need some new chalk, otherwise I'll be writing with my fingertips. Okay, here we go. Now, if we have an arbitrary linear map, linear maps behave interestingly with respect to linear subspaces. Namely, if we take U to be a linear subspace of V, then the compatibility of F with the additions and scalar multiplications implies that the image of U under F, so F of U, so just to recall, this I did, I think, in chapter 1 of my previous course. This is the set of all f of u as elements of w where u is in u. So all elements that we can achieve by as images of points in u under f. So this is also a linear subspace. This is a linear subspace of w. So to summarize this, linear maps map linear subspaces to linear subspaces. And the same goes in the other direction. Namely, if U prime is a linear subspace of W, then its pre-image, f to the minus 1 of U prime. And this is now the set of all V in V that are mapped to U prime under F. So this is the pre-image. All the points that are mapped into U prime, so as a subset of V. And if this is a linear subspace, then also the pre-image is a linear subspace, this time of V. Okay, so images and pre-images under linear maps of linear subspaces are again linear subspaces, which is beautiful because this shows really the kind of the linear structure is preserved in many ways by linear maps. Okay, let's prove this. Okay, first of all, so we need to take, simply need to show that this has linear subspace properties. So first of all, we need to show that sums of vectors in f of u are again contained. So we take two elements w1, W2 of f of u. So since they are in the image, we can of course find elements of u which map onto these ones. So take u1 and u2 in u such that f of u1 is w1 and f of u2 is w2. Then the sum of w1 and w2, which we need to show to be in the element of f under u. So this is, by definition, f of u1 plus f of u2. Now, f is linear, so this can be written as f of u1 plus u2. But now, since u is a linear subspace, this sum of these two elements needs, again, to be an element of u. So this is an element of u by the linear subspace property. So this element, this point lies in f of u, which we wanted to show. So the sum of these elements lies again in f of u. Now for scalar multiples, it's basically the same way. Moreover, for all lambda in k, we get that if we just recycle these vectors w1 and u1, so I don't need to introduce them again. Lambda times w1 is the same as lambda times f of u1, which is, by the linearity of f, the same as f of lambda times u1. But since u1 lies in u, this is a scalar multiple of u1, and u is a linear subspace. This again lies in u. So this is again in f of u. And this already shows the claim. So here we only needed the linearity of f here explicitly and the linear subspace property of u at this point and at this point, so to show that they are again contained. So this shows f of u is a linear subspace of u, of w. Okay, now for the other direction. It's basically the same proof. So we take v1 and v2 in the pre-image of u prime. Okay, and put, so then if we take u1 and u2 are elements of u prime, where u1 is the image of f under image of v1 under f, and u2 is the image of v2 under f. So simply since they are in this pre-image, these are in u1. So we need to show that the sum of these two is in this pre-image. So we need to show that the image of v1 plus v2 under f lies in u prime. Now, how do we see this? Again, linearity, this is, and so I'm not writing now down every single time using linearity, since this is pretty obvious at this point. So this is the same as f of v1 plus f of v2. This is by definition u1 plus u2, and these two are in u prime. U prime is linear subspace, so this is in u prime, since u prime is linear subspace. So this shows f of the sum lies in u prime, and in other words, f v1 plus v2 lies in the pre-image of u prime under f, and lambda v1 in the pre-image of u prime for all lambda in k. This is shown analogously. Don't do this computation again. So same thing, so here we get then that lambda u is in u prime, so the linear subspace property, just the other property, saves the day at this point, so this follows analogously. So this shows that f to the minus 1 of u prime is a linear subspace of V. Okay, so this is an interesting property, and as a next thing, we will take a look at two special cases that are very important. They tell us a lot about linear maps. So two spaces that are constructed in this way, so as an image or as a pre-image of a linear subspace. And yeah, let me erase and then we shall see these constructions.